Okay, fine. So I welcome you all again, and in the last class we looked at derivation of RANS equation. The so-called Reynolds average Navier-Stokes equation was derived by taking Navier-Stokes equation and then Reynolds decomposition and ensemble averaging. With that we achieved RANS equation. The only thing is, in RANS equation we got extra unknowns. So the RANS equation looked like you had dou ui bar by dou t plus uj bar. I am just rewriting what has been already derived, right, equal to the mean pressure gradient dou p bar by dou xi plus I have dou by dou xj of, or I can say mu dou xj ui bar, the viscous stress tensor, and the Reynolds stresses ui prime uj prime. I am just rewriting the equation. What was the equation number for this, if you remember? 7. Okay, so this was equation number 7. So this equation is perfectly fine for those who want mean velocity and pressure in engineering applications. The only problem is this particular term. Okay, you have extra unknowns here, 6 extra unknowns due to the Reynolds stresses appearing. So now there are two ways of going forward. One option is of course to model them. Okay, option one is to model Reynolds stresses. That is your ui prime uj prime over bar, model Reynolds stresses to close equation 7 and therefore solve them once the equations are closed. This we will see. This particular option and its methodology is what is called RANS models. RANS model, that we will see later. The option 2 is of course to derive a transport equation for the Reynolds stresses. Okay, to get a transport equation for Reynolds stresses ui prime uj prime. That means 6 extra equations. So that is one theoretical way of looking into it, and this is the direction Osborne-Reynolds took, deriving an equation for the Reynolds stresses to see whether that is closed. If that equation is closed, then you do not need to model anything. Okay. For that we have two different options. There are two ways of deriving this Reynolds stress equation, and one leads more unknowns than the other one. Both are of course derived from first principles. We have not made any assumptions so far. No modeling has been done. We have used only Navier-Stokes equations. And if you start from one of the equation, it leads to more unknowns than the other. Okay, so the starting point for derivation matters. So we will do the one which gives least number of unknowns because we need to model, right? So the modeling community chooses derivation of this Reynolds stress equation in a different way, and the starting point is an equation for fluctuating fluid motion, right? We have done the equation for mean momentum. Now we look into fluctuating momentum. That is the starting point. Okay, so we had two options. So we will go ahead and take option 2 first to see what happens. So that is the equation for fluctuating fluid motion or your fluctuating momentum. So the mean momentum equation is already there, which is your RANS equation. So now all I have to do is take one equation, which is Reynolds decomposed Navier-Stokes equation. Take Reynolds decomposed, not averaged. So you are essentially taking Navier-Stokes equation and decompose it into mean and fluctuation. Okay. So Reynolds decomposed Navier-Stokes, and then minus of the RANS equation. So basically you take out the RANS equation terms, subtract them from the Navier-Stokes. Navier-Stokes is the instantaneous and the mean to get the fluctuation, right. So this is your, so what I do is, this is the RANS equation minus RANS equation. So this is your mean part and this is your instantaneous. Instantaneous minus mean should give you the fluctuations, and that is what we want, an equation for fluctuation ui prime. Okay. So if you recollect the Reynolds decomposed Navier-Stokes equation, what was the equation number there? The momentum equation. Okay, let me write the equation, then you tell me what it looks like. So I have the decomposed equation of the form dou ui bar by dou t plus dou ui prime by dou t plus, I have the 4 convective terms here, which is uj bar dou ui bar by dou xj plus uj bar dou ui prime by dou xj plus uj prime dou ui bar by dou xj plus uj prime dou ui prime by dou xj. Only Reynolds decomposed, no averaging here, because we want the instantaneous Navier-Stokes equation, right. And this is equal to, we have splitted the pressure term also into mean and fluctuation part. So dou p prime, dou p bar by dou xi minus 1 by rho dou p prime by dou xi, and the 2 viscous terms, which is nu dou square ui bar by dou xj plus nu dou square ui prime by dou xj. What was the equation number for this? We have, there was no number for it. Okay, fine, no problem. So now we have to simply take equation star minus equation 7. That would give us our equation for fluctuating fluid motion. Okay. So if I just copy this part, okay. So I have, if I have the equation minus of this, so I have just copy pasted equation 7 here. So let's just write this as these equations. So I would get, okay. So if I do this, I'm going to write it here. What this implies is this equation star minus equation 7. So we already see certain terms cancel out, straightforward, this minus of this, and then we have the mean pressure term going away and the mean viscous stress terms goes away. Okay, right? So I have now we'll write out the rest of the terms that is available here. So we have about so before that I would like to have this equation. Let me see. Yes, so I would like to have this last term written in a different way. Okay, so this we used a trick to get this term, push the fluctuation inside the differential operator. Before that it had its own original term, so I'll retain that particular term here, which was your uj prime dou ui prime by dou xj average. Upon ensemble averaging you got this particular term, then you added that trick using continuity plus 0 to push this inside using chain rule. So I am retaining the original form. So this minus this, so what are the terms that is coming out is basically I have dou ui prime by dou t, this is your equation 7. So the equation for fluctuating fluid motion, I have one unsteady term, there is a convective term plus uj bar dou ui prime by dou xj, and then I have on the left hand side one of this is gone, so two more extra terms are there, this and this, right? So I would take it out onto the right hand side. So I'll write the pressure term first, fluctuating pressure term dou p prime by dou xi, and the viscous term plus nu dou square ui prime by dou xj square. Sometimes I write dou xj square, this is not the actually, it's just a my own convention. Many times people write it, but it actually means dou xj dou xj. Okay, the rest of the terms is, this is plus minus of this, so I get so this becomes still, so this becomes minus here, coming on to the other side, minus uj prime dou I bar by dou xj minus uj prime dou I prime by dou xj, and then this minus of this will be positive, so this takes the positive form here, plus uj prime dou ui prime by dou xj average. Okay, or I can simply rewrite this as minus of, I can say minus of this so I got an extra equation for fluctuating fluid motion. That means if you are interested to study turbulence itself, not the mean velocities but fluctuating velocities, u1 prime, u2 prime, u3 prime, you have an equation from first principles here, and at least the first 4 terms looks fine, they look lot similar to your Navier-Stokes equation, except that it is prime instead of an instantaneous velocity, an unsteady rate, convective rate, pressure gradient, as well as the viscous term, but it has 3 extra unknown terms that has come onto the right hand side. One of them is of course the Reynolds stresses, the last one. So one when you derive this equation, one easy way of finding out whether the derivation is correct is, if you average this, all terms should vanish because its average of the fluctuation is 0. So you have to check this thing. So note, upon averaging is this equation 8? The last equation was 7, right? So let's call this equation 8. So upon averaging, all terms in equation 8 must vanish. That is if the derivation is correct. So that you can easily see, the first one, average of the fluctuation is gone. So first is okay. The second one, uj bar is statistical. So average of the second term is 0. Pressure gradient also, average of P prime is 0. Ensemble averaging of Ui prime is 0. This particular term, averaging of Uj prime is also 0. And the last term, if I average this, is it 0? That is not 0, right? If I average the bracketed term, in the bracketed term, the first term in that part, if I average it, that is not 0, because it is correlation term. But the second one inside the bracket is the Reynolds stresses. So it is Reynolds stresses minus Reynolds stresses, it goes to 0. So all terms must vanish if you have derived the equation right. Okay, that's an easy way of checking. So we have an equation 8. So what? I mean, does this solve the turbulence problem? So we will see here again that how many equations and how many unknowns are there. How many equations and how many unknowns. So I have got 3 extra unknowns, 3 equations, sorry, which is for my u1 prime, u2 prime, u3 prime. Okay. I have the fluctuating continuity equation also, right? Using that I can get an extra equation, not a problem. One extra equation to get a fluctuating pressure. So here I have same thing, it's u1 prime, u2 prime, u3 prime, that is my ui prime, 3 unknowns. I have p prime, that's one unknown, but p prime you can also get an equation for it using continuity equation. You have continuity will give 3 plus 1. So p prime can be taken care of. In addition to that, I have, how many unknowns are there now? I have the Reynolds stresses anyway, the uj prime dou ui prime by dou xj. This is anyway giving me 6 unknowns. In addition to that, I have the other term, the first term of the bracketed term, that is giving me another 6. The uj prime dou ui prime by dou xj. This is not a statistical term. It is not a correlation now. This is another 6 unknowns, 6 or 9. 9 is total, but it is a symmetric tensor, so 6. Again you have less equations compared to number of unknowns, and the number of unknowns is growing. In the RANS equation you had only 6 unknowns, but now you got extra 12 unknowns. That's why it's called turbulence closure problem. More you average, more you try to dig deeper, more unknowns pops in. It's an endless exercise. Okay. So again you have equations less than unknowns, the turbulence closure problem.